Sampling distributions. This chapter or segment of our course is very fundamental in the framework that we are going to approach, which is that of inferential statistics. Up until this point, we have learned descriptive statistics, ways to describe samples, and we've also learned probability properties. All of that was essential to the foundation of sampling distributions and then inferential statistics. And we will discuss all these aspects here in the corner in due time. One of our overarching goals in data analysis is to learn about a population and features of that population. There's all sorts of features to learn about. Often we focus on quantitative features such as the mean and median, standard deviation, etc. There are other features as well. And in the beginning of our course, we discussed how we collect information from samples to learn about populations. However, there are discrepancies between samples and populations, and that's to be expected, and those discrepancies we called sampling error. And so an overarching goal is to distinguish between features that are present in samples that are reflections of the population and features that may be only due to chance effects, right? Those are the discrepancies. And so we're going to develop the background, it's highly theoretical, that allows us to put limits, specific limits on the degree of sampling error that is expected in a study. This is with this idea of sampling distribution. And this is very fundamental in moving us from descriptive stats, which is what we've been doing, all the way to inferential stats. So that was a somewhat quick overview of where we are headed and why, but now let's discuss sampling variability. Sampling variability is variation across samples, even though they came from the same population. And so we know this exists. Sample to sample are going to be different. And so a sampling distribution is going to characterize that variability. And it's going to do so with a particular statistic in mind. So for us, at the moment, we're going to focus on the sample mean, but in due time, we will also look at another statistic, that called the proportion. In practice, generally for a study, depending what is going on, you're not collecting many samples. You're collecting lots of info from different individuals, hopefully, but you usually just collect one sample that consists of many individuals. Techniques may vary. And so what I'm about to walk us through is a sort of theoretical idea here, where I would like you to imagine collecting many samples, all of them actually, from a population of some size, doesn't really matter. And so you got sample, and then compute a sample mean for each and every one of them. So you might have sample mean 1, you got sample mean 2, sample mean 3, and 4, and 5, and 6, and many, all of them. It's a lot. You don't generally go and do this, but we need to think about all these theoretical sample means. the distribution of all of these sample means. Remember, they would just be numbers, right? So we could graph them and they would form a distribution. That distribution is this thing called the sampling distribution. If we were to graph this, it would form a smooth curve. Now I'm just going to draw a normal one. It doesn't necessarily have to be normal, but that is ideal. And I wouldn't label this y and I wouldn't label it x, right? Those are our two main letters. But I would actually need to label it y with a bar or x with a bar, because this would be the distribution of not individual observations, but sample means. And we want to know how this distribution looks. It could be skewed as well. We'll talk about that. But we like it when we're working with bell-shaped distributions, right? And we want to talk about where would the center be located? And could we put a number there or some characteristic there? And we would also like to know, yes, but we would also like to know how spread out is this distribution of all possible sample means. If I were to label a few tick marks on here, I can't really use numbers right now, but these tick marks would represent different values of sample means, right? Maybe that's sample mean 18, I don't know. So we could actually talk about, well, what would the center of all these sample means be? Wouldn't the mean or the average of all sample means, we discussed this once, wouldn't it be the population mean? And so where we are headed is addressing this question of, well, I want to learn about population means, right? That's mu, and that's unknown. Unknown pop mean. And how close to mu is our sample mean, which is known because it's from a sample. Now, we actually cannot answer this top question because this is a lowercase x bar and it's a particular value from a particular sample. We actually cannot answer that. However, here I've got capital X bar, which is about this distribution. It's the sampling distribution of all possible sample means. And this is because we will be considering X bar, the distribution of sample means, in a theoretical construct. And the answer to this question is essentially provided by this theoretical distribution. Let's characterize features of this distribution, the sampling distribution of the sample mean. We're going to do this by discussing its shape, its center, and how spread out it is. Let's start with the center, our favorite descriptor of the center, the mean. The mean of all possible sample means is denoted as the mean of all possible sample means. That's going to be X bar is the true population mean. Hopefully that makes intuitive sense. I know this notation looks kind of repetitive, but this is saying that the mean of sample means is the true parameter, the true population mean. So that would be the center. Let's move on to spread. The mean's best friend, standard deviation. Standard deviation of the sampling distribution. This doesn't quite translate as nicely as the previous box there, but the standard deviation of the sample means is, it's not just the spread of the population, because sample size plays a very important role in the accuracy of the sample mean in estimating the population mean. And this may seem unintuitive at first, but hopefully we can sort of validate this, because we know that with larger sample sizes, we learn more about a population in the sample. And so we would expect sample statistics from larger sample sizes to perform better as estimators to their respective parameters. And that's sort of why n is in the denominator here, because as n increases, the denominator increases, this whole number decreases, indicating that the spread of the sample mean is less and will better approximate the population mean. Another way to put this would be that a smaller standard deviation of the sampling distribution, smaller values of that would mean smaller expected sampling error, and thereby resulting in a sample mean that is a better reflection of the population mean. Now let's discuss the shape of the sampling distribution of the sample mean. We love dealing with normal distributions, and so we want to discuss under what circumstances will the shape of this distribution follow a normal distribution. Well, there are two ways in which this could be satisfied. A, if the population from which you are collecting these theoretical samples, if that population is normal. I hope that kind of makes sense. Like if the source, the baseline population X is normal, and we'd expect samples from that population to be normal, and thereby all sample means to follow a normal distribution. There is another way that this can happen, because sometimes you don't know the shape of the population distribution. That could be pretty prized knowledge. So we do have another way that this can be satisfied. Or, regardless of the shape of the population, as long as you have a sufficiently large sample size, then that is enough to assume that the sampling distribution of the sample mean is approximately normal. This may warrant a little more explanation. I will need more space. Part B here is referred to as the central limit theorem, CLT, and it is probably more often used in practice than Part A, because often it is unknown what the population distribution may look like. And so what is a sufficiently large sample size? The answer to that depends on the distribution that you're working with. For instance, a distribution that only mildly deviates from normality may not require a super large sample size compared to a distribution that is very skewed. For the purposes of our course, we're going to put a pretty conservative number on this just to kind of blanket the all possible reasonable scenarios for our course. And so we're going to use or presume that a sample size of 30 or more is going to be sufficient to implement the result of the central limit theorem. And why is this so important? It's because of the utility of the normal or bell-shaped distribution in the validity of inferential techniques that are to come. Okay, well, what now? How are we going to implement all of this info and utilize it in some meaningful way? Well, because we want to make probability statements about sample statistics, we're going to end up using this in the formation of a z-score. Just like we did previously, where we had the z-table and we use the standardization formula to create a z-score. And that's what we're going to do here as well. It's just going to be slightly different. But let's draw some parallels. So previously we used the z-score of x minus mu over sigma, and this allows us to transform the variable x into z. And this is usually applied to individuals, right? We like, what's the probability that an individual is greater than 6 inches? Or we might ask, what proportion of the population is larger than 6 inches? Visually, right, we would have a variable, hopefully distributed normally, and we presumed we know the mean, and we would find the tick mark of a particular x value and transform that into z in order to find, say, the probability to the left or to the right, in between, whatever. So that feels familiar, right? Now we will use that same idea, except our z-score is going to be not an individual x value, but a sample mean x bar. We will subtract not just the mean mu, but the mean of the distribution of x bars. And in the denominator, we have sigma yet again, but it is the standard deviation that applies to the x bars. Now, this is going to be an important little formula, but I'm going to take it one step further, and because this is a formula that refers to previous formulas from just a few moments ago. So I'm going to replace a couple terms in this red text here. This mu with the sub x bar, we can simplify that greatly because it's just mu referred to a few minutes ago. Here in the denominator, we're going to replace that with sigma over square root of n. the z-score formula here, x bar minus mu over sigma over square root of n. And this is the one that I'm going to put in a nice little box because we will use that a lot. And just like we did previously, what we will do is take any sample mean of interest, transform it into a z-score, and then utilize the z-table to acquire probabilities. And we will look at some examples in the next video. See you there.